All right, so welcome to our little workshop today. We're going to be going over basically just drawing Lewis structures. So a quick little recap on counting valence electrons. So remember that we can use dots to indicate that there's a valence electron on a Lewis structure. And so how do we determine the number of valence electrons based on their groups? So you can see here that there's going to be hydrogen right here, and then we can see it's under group 1A. 2A for beryllium and everything else below it, and 3A, 4A, and so on, all the way up until AA. And basically that letter, that number that appears right next to the letter A is going to basically indicate how many valence electrons we have. So for example, if I were to pick some random element like Te down here, it is under column 6A. So therefore, tellurium should have 6 valence electrons. So a little practice. So how do we determine how many valence electrons, say, in lithium? So we see lithium here is under group 1A, so therefore it's going to have 1 valence electron. So we can represent this in this following Lewis dot structure. Li with a single dot. Now how about bromine, Br? So if we look around on the periodic table, we can see it is under group 7A. Therefore, bromine should have 7 valence electrons. So we can indicate it by drawing, I just read the chemical symbol. And then when we do our valence electrons, remember that we always want to do one around each side first and then close them or pair them up at the end. So 1, 2, 3, 4, 5, 6, 7. And so this is going to be the Lewis dot structure for bromine. Let's look at gallium. That one's going to be under group 3A. So therefore, gallium is going to have a total of 3 valence electrons. So we can do 1, 2, 3. Next, we have silicon. Silicon's just right over here. Silicon's under group 4A. So therefore, silicon is going to have a total of 4 valence electrons. So remember, we always do 1, 2, 3, and 4. You don't want to write it as something like this, where you do 1, 2, 3, 4. This is going to be incorrect. So you want to avoid drawing your Lewis dot structures like that. Finally, we have calcium. Calcium is going to be under group 2A. Therefore, calcium is going to have a total of 2 valence electrons. So we can represent calcium as Ca with 2 dots, one on each side, or one on basically one of the 4 sides. So Lewis structures, remember that they show the connectivity and the bonding between atoms. And they basically show the bonding between atoms in a molecule, along with any electrons that may exist within them. So for example, if I were to draw the Lewis dot structure of nitrogen, then we can draw it like this. We can draw N, and then we can just count. Nitrogen is under group 5A, so we can just do 1, 2, 3, 4, and then 5. And just remember that you don't ever want to draw your Lewis structure like this, where we do 1, 2, 3, 4, 5. This is not the correct way to draw it. All right, so moving on, we have the octet rule. So the octet rule basically states that atoms usually want to achieve a valence electron count of 8 in their outermost shell. And they can do this by either sharing or transferring their electrons. So that would be like covalent bonds or like ionic bonding, basically. And they want to be kind of like their nearest noble gases because having a filled octet greatly increases the stability of the atom. Now, there are some exceptions that do apply. We do have something like hydrogen, for example. Hydrogen, it does not need to fill a valence electron count of 8, and instead it can just get to 2. So let's say we have some molecule like this. We can just do a total of 2 valence electrons. So this bond represents 2. And then we could probably put like another one here, another one here, and another one down here. So hydrogen only needs to form 1 bond to get that noble gas configuration, basically. But then if we look at carbon, we can see carbon has a total of 2, 4, 6, and then 8 valence electrons due to basically sharing or transferring the electrons to a neighboring atom. Now, if we look at boron, boron is actually another example in which the atom basically does not need to reach a complete octet in order to be stable. So a possible boron molecule, we can do something like BH3. So boron only actually needs a total of 3 bonds in order to achieve that noble gas configuration, and then it would be pretty stable. So we can just do 1 boron bonded to a hydrogen here, bonded to another hydrogen down here, and 1 more hydrogen bonded up here. And so that would be like an exception of where boron and hydrogen does not actually need a complete octet. And so they're kind of like exceptions to the rule. All right, so just some general pointers or like tips that I like to use when I draw Lewis structures. So group 1A and 7A atoms. So an example of a group 1A atom is like sodium. And a group 7A atom is basically any halogen. So we have fluorine, chlorine, bromine, iodine, and so on. And these only form 1 bond in most cases. So as a result, these group 1A or group 7A atoms, they're usually going to be terminal. So if you look at aluminum, for example, we can see that aluminum is going to have a connectivity that looks something like this. And so why is that? That's because if we were to draw the Lewis dot structure of chlorine, chlorine will have a Lewis dot structure that looks like this. So we do 1, 2, 3, 4, 5, 6, 7. So there's only 1 unbonded electron pair, or 1 unbonded electron here. And then because of that, it can only form 1 bond basically. So then we can look at something like aluminum, which would have 3. And then we can just draw a connection right there. And then we can do that for all the other chlorines, basically. Moving on, so if an atom does not have a full octet, you can actually just form double bonds and triple bonds if possible. So let's say we have nitrogen here, or nitrogen gas, so that would be the formula N2. So if we're to draw the Lewis structures of each nitrogen, we can just draw 1, 2, 3, 4, 5. And then we can also do another one here. 1, 2, 3, 4, 5. So we can draw one bond here. And if we draw that one bond, we can check to see if they have a filled octet yet. So we can do a count. So this will be 1, 2. Oh, sorry. This will be 2, 3. This entire bond will count as 2, so there'll be 5. And then the single one is 6. So this does not have a filled octet. So what we can do instead is we can see that there's going to be an unpaired electron on the top of this nitrogen here. And there's also going to be an unpaired electron on the other nitrogen. So since they're unpaired, we can just basically draw a connection between them. And then we can do another one down here because there's also another unpaired electron. And if we do that, then we get a triple bond in between the two nitrogens inside the nitrogen gas molecule. So the final Lewis structure would basically look something like this. And my last little tip is that you want to count your valence electrons on your structure so that you can basically confirm your structure. And remember that there are going to be more than one possible structure for certain molecular formulas. So if I were to count the valence electrons on, let's say, this ammonium ion right here, I know that nitrogen usually has a valence electron count of 5. And then hydrogens have 1 valence electron each. So I can do 1 plus 1 plus 1 plus 1. So that would be 4. So currently we have a total of 9 valence electrons. But remember that we have a plus charge up here. So we can actually subtract 1 valence electron. So our final molecule should only have a total of 8 valence electrons. So if I were to draw a structure that is possible for nitrogen, I could draw something like nitrogen being the central atom. And then I'm just going to draw all the hydrogens around it. And remember that there is 1 electron missing from like normal. And so because of that, we had to take away an electron from somewhere. You usually won't take it away from the hydrogen. Instead, I will take it away from nitrogen. So I can just draw 1, 2, 3, 4 rather than 5 valence electrons. And then remember that hydrogens have 1 valence electron each. And then I just like to connect the dots. And remember that we have a plus charge on the ammonium ion, so we do need to indicate the plus. So we can put the plus charge right here. And so if we do a valence electron count on this proposed structure, we can see that it has 2, 4, 6, and then 8. So this structure has 8 valence electrons. And then if we compare that to our little calculation before we drew the structure, we can see that we also got 8 valence electrons. So that's how we basically confirm that we got the correct structure. All right, so a little practice. So you can pause or try these out on your own. And basically, I want you to try and determine whether or not the following atoms or molecules are reasonable or valid Lewis structures. So this first one, I'm going to give you a minute, and then we can go over some of these. All right, so I'm going to go over this first one. This is Br with a 2- charge. So this looks a little bit unusual because bromine is a group 7 atom. So in order for bromine to reach its noble gas configuration or noble gas electron count, we would have to add 1 electron to it. So we can go from 1, 2, 3, 4, 5, 6, 7. So then bromine, in order to get the noble gas configuration, so we will just add 1 more electron, which would make this a minus charge. And then if you compare that to our original structure or the original proposed structure, we can see that this 2 minus charge is not possible. Because if we were to draw this one out, we get something that looks very unusual. We might get something that looks like this: 1, 2, 3, 4, 5, 6, 7. And then we need to add 2 more somewhere. But if we add this 1 more, we don't know where to add that very last one. So this really wouldn't be possible. You can't just throw in another one like that. So you don't want to do something like that. Next, we have the Lewis dot structure of carbon. And so carbon is a group 4 atom. Therefore, carbon should have a total of 4 valence electrons. So if we do a little count, we have 1, 2, 3, and then 4. So that looks good so far. And remember that we always do our valence electrons one at a time, and then we close them or we pair them at the end. So we do 1, 2, 3, and then 4. So this structure looks good. Next, moving on to number 3, we have this pretty large molecule. So I'm going to do a little count on each one to make sure that each one has a proper number of valence electrons. So if I do this carbon right here, we can do 1, 2, 3, and then 4. So that would be 4 pairs, therefore 8 valence electrons. This carbon looks possible. It looks good. We can check this carbon right here. We can do 2, 4, 6, 8. This one also has 4 valence electrons. Now, if we count this top one up here, we can do 2, 4, 6, 8. So this one also has 8 valence electrons. So this top carbon is good. And then finally, if we count this central carbon, we can do 2, 4, 6, 8, and then 10. So 10 is going to break the octet rule. Therefore, this is not going to be a very reasonable Lewis structure. So this central carbon here breaks the octet rule. So this one is going to be not a very valid Lewis structure. Finally, we have this molecule on the bottom. This is going to be the molecule SF6. This is the proposed molecular formula and structure. So what we can do here is we can do a valence electron count. So we can do sulfur has 6, and then fluorine has 7. So we can do 7 times 6, and then we get 42. So then if we do a little count, we can do 2, 4, 6, 8 right here. So fluorine has a total of 8. We can do another one. 8, 8, 8, 8, and 8. So we do a total of 42 plus 6, we should get 48. And we have 6 groups of 8 on this structure down here. So we do also have a total count of 46 and 48. And so this looks like a possible and reasonable Lewis structure. And so you might think that sulfur, if you do an electron, valence electron count, it might break octet. So you see 2, 4, 6, 8, 10, 12. So sulfur has a valence electron count of 12, which seems a little bit unusual. But then this goes back to that weird rule where not all atoms technically obey the octet rule, and sulfur is actually one of them. So sulfur can also make 6 bonds, which does seem unusual. Another possible structure that you may have seen is something like phosphorus. Phosphorus can make 5 bonds. PCl5 is an example. And so generally the rule is third row elements can sometimes exceed octet rule. That's just a little unusual violation of the octet rule. All right, so now we're gonna do some practice of actually drawing these Lewis structures. I'm gonna give you guys like a minute. You can pause and then try some of these out on your own. So I'm gonna go over the first one. This is lithium. Lithium has a element symbol of Li. And remember that lithium is a group 1 element. And because it's a group 1 element, we can just draw 1 valence electron. And so that's just going to be the structure for lithium. Nitrogen, I believe I drew this one earlier. So if you have nitrogen here, nitrogen is a group 5 element. So we can do 1, 2, 3, 4, and then 5. So that's going to be the Lewis structure for nitrogen. Moving on, we have ammonia, which has the element molecular formula of NH3. So hydrogens, they are usually going to be terminal, so they're going to be on the endpoints. So what I like to do is I like to draw out the Lewis dot structure of each atom. And remember that nitrogen has 1 more lone pair up here. And so we know hydrogens tend to be on the endpoints of the molecule. They're not usually going to be in the middle. And so if we just lay out the structure of each individual atom, we can see that there's going to be a lot of possible unpaired electrons that we can just pair and then form bonds. So we can bond this electron. We can bond this electron. And then we can bond these unpaired electrons. All right, the last one we have is formaldehyde. So formaldehyde is going to have the structure CH2O. So what we can do here is we can basically draw all the individual Lewis dot structures. And hydrogens tend to be on the endpoints. And then I can draw a structure for carbon. So we can do like 1, 2, 3, and then 4. And then we can also draw oxygen. Oxygen has a Lewis structure that looks like this. 1, 2, 3, 4, 5, 6, because it's a group 6 element. And what I'm going to do here is I'm going to draw this unpaired electron and bond it here. I can draw another bond right here. And then I can also draw one bond up here. And then we can see that the octet is not actually completely filled. So if we do electron count on the central carbon, we can see that there's going to be 2, 4, 6, and then 7 right here. This one also, if you count the oxygen, we have 2, 4, 6, and then 7. So both carbon and oxygen do not have a filled octet. So what we can do here is we can basically just join these unpaired electrons, and then we can form a double bond. So our final structure of formaldehyde would look something like this. All right, so moving on to the last few problems. These last few problems are going to be a little bit more difficult. So draw the Lewis structures for the following atoms and molecules. So for this first one, we have boron trifluoride. And I'll give you a few moments to try these out on your own. All right, so for this first one, we have boron trifluoride. So this has a formula of BF3. Remember that halogens, so fluorine, chlorine, bromine, and iodine, these are going to be, typically they're going to be terminal. So then what we can do is we can draw the valence electrons or the Lewis dot structures of each one. I have another fluorine here. 1, 2, 3, 4, 5, 6, 7. We have one more fluorine. It's going to be 1, 2, 3, 4, 5, 6, 7. And then remember that boron is going to be one of those violations or exceptions to the octet rule. So we can draw boron in the center, and boron is a group 3 atom, so it can form a total of 3 bonds. So if we draw the connectivity, we can just connect these unpaired electrons between fluorine and boron. So we can do one here. We can do another one up here. And then one more down here. And so our final structure would, if I were to draw a little bit more neatly, it would look something like this. Our next one, we have C6H6. And so this is definitely going to be one of those examples where you can get multiple structures and they'll be correct as long as you don't violate octet and you have proper valence electron count. So I'm going to draw one of the possible ones. There's going to be probably like 2 or 3 that I can come up off the top of my head. So the most familiar one I know is probably going to be benzene. So we can draw a structure that looks something like this. And then basically we just have alternating double bonds. And then in order to fill up octet, we can just make sure each carbon has 4 bonds. And we can do that by just basically throwing in hydrogens. So this is a structure that I'm usually familiar with. There are certainly more. For example, I could draw a non-circular or non-cyclic compound. So I can draw something like 6 carbons in a row. And remember that each carbon has a total of 4 possible bonds. So what I can do here is another possible structure is I can just throw in a hydrogen here and bond it. I can form another bond right here. So that will make a double bond. And then we can throw in another hydrogen right here. And then another one we can throw in is we can throw another hydrogen down here. And then another bond that we can form is basically the same thing, but on the other side. So I can throw in a hydrogen up here. We can also throw in another hydrogen down here and then form a double bond here. I can add one more hydrogen down here. And then we can also form a triple bond. So we can form one that looks like this with these unpaired electrons. So the structure looks a little bit weird. If I were to draw this more organized or more neatly, it would look something like this. So this is one possible alternative answer. There's probably a few more that you could draw. There's a lot of them basically. But in order to just check to make sure you have the right answer, what we can do is count the valence electrons and then make sure that your structure that you draw has the same number of valence electrons. So we can do C6 and H6. So C6, each carbon has 4 bonds. So we can do 4 times 6. And that will get us 24 valence electrons. Hydrogens have 1 valence electron each. So we have 1 times 6. And then we would just want to make sure we have 30 valence electrons total, because we do 20 plus 6 to get us 30. So if we were to do a little count, we can count the valence electrons on like this structure on the left of benzene. We can do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and then 30. So that's how we know that the structure of benzene is correct. And if we were to draw or check the other answer, we can do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and then 30. So this is also a possible structure. So you know that this one is correct. And yeah, so there's probably a lot more structures you could draw, but those are just some of the possible ones. So let's look at the next example, CH3COOH. So this one is going to be acetic acid, which is also known as vinegar. So I'll give you a moment to try this one out. All right, so we're gonna draw the structure of acetic acid. So what we have here is, I like to just usually put carbon as the central atom. So I can draw carbon right here. And then carbon is going to have a total of 4 valence electrons. So we can do 1, 2, 3, and then 4. And then what I like to do is I will probably draw in the oxygens. So I can draw the Lewis structure of oxygen, 1, 2, 3, 4, 5, and then 6. I can draw in another oxygen somewhere. So we can draw one like this, 1, 2, 3, 4, 5, and then 6. Oxygens are usually going to be terminal, so I like to put them anywhere. Hydrogens are usually going to be terminal, so I like to put them anywhere around the ends. So I'm just going to put in a hydrogen here. And I'm just going to probably get started on the connectivity now, so I know where I need to add more bonds. So what I can do is I can draw one bonding set of unpaired electrons here. I can draw another bond right here. And then I can also draw another bond that goes from this carbon to this oxygen on the right. And then this oxygen on the right, I can also draw one more bond that goes from here to the hydrogen. And then what we've basically drawn so far is we've actually just drawn the COOH part. The next one I'm gonna try and draw is I can basically put CH3. So I'm gonna draw 4 valence electrons. 1, 2, 3, and then 4. And then I'm going to draw the hydrogens. Once again, they're going to be terminal. And then I can just bond these unpaired electrons here. 1, 2, 3. And then we can see that this CH3 on the left side has 1 unpaired electron here. And then this COOH fragment on the right also has 1 unpaired electron down here. So we can actually join these 2 unpaired electrons. So the structure looks pretty messy. I'm going to redraw it up in the top right-hand corner. So the final structure of acetic acid would look something like this. So this one up here, that is going to be a more cleaned up version of what the structure for acetic acid is going to look like. And this final question, we have number 8. This is going to be SO2. So this is going to be sulfur dioxide. So you can try this one out, and I'm going to go over it in a moment. So sulfur dioxide is going to have 2 structures that I can probably think of. They're both going to be technically the same. So this first one I can draw is going to look something like this, where I can draw sulfur with 6 valence electrons. And remember that sulfur is one of those unusual elements that can violate octet rule. So I can draw it like this. I can draw an oxygen down here. So I can do 1, 2, 3, 4, 5, 6. And then I can do another oxygen down here. I can do 1, 2, 3, 4, 5, 6. And this may seem unusual, but these 4 valence electrons surrounding sulfur can each form their own bond. So these 4. And because of that, we can actually draw the connectivity of this oxygen going to this sulfur, this one going here, and then this one going here, and then this final unpaired electron going to this oxygen's unpaired electron. So we would end up getting a structure that looks something like this if I were to clean this up. So this would be one possible structure of sulfur dioxide. You can actually draw another one where we can avoid breaking the octet or violating the octet rule on sulfur, because if you do a count on sulfur's valence electrons, we can see that it has 2, 4, 6, 8, 10, and that looks a little bit unusual. So an alternative we can do to this is we can still leave sulfur as our central atom. And then what we can actually do is we can basically do something called a resonance structure, which will allow us to move one of these double bonds onto the oxygen. And as a result, sulfur is going to lose 1 electron. So I'm going to highlight this. And then oxygen is going to gain 1 electron because it's no longer sharing it in a bond, not really. So if I were to draw that final structure, you could get a structure that looks something like this. So we can see that this structure of sulfur dioxide has both a plus and a minus charge. So that will cancel out. And then we can see that there's no net charge on the molecule that we drew, and there's also no charge on the molecule at the beginning of the question. So this is also going to be another valid structure for sulfur dioxide. We can always confirm our answer by counting our valence electrons. So if we do a quick count, we can do 2, 4, 6, 8, 10, 12, 14, 16, 18. So this bottom structure has 18 valence electrons. If we do the same thing down to this structure of the resonance structure up here, we can do 2, 4, 6, 8, 10, 12, 14, 16, 18. So this structure is also going to have 18 valence electrons. And so that is actually going to be another structure that you can draw for sulfur dioxide. All right, so that actually concludes our little presentation, our little workshop on drawing Lewis structures. If you have any questions, you can always schedule for tutoring. And if you haven't already, you can join the virtual STEM Center on campus. And you can always email the Natural Science STEM Center and then follow us on Instagram or Facebook. And yeah, if you have any questions, feel free to ask.